What is a DC motor? How does it function and its application? A DC motor, direct current motor, is an electrical machine that converts electrical energy into mechanical energy, rotational motion, using direct current, DC. It is one of the simplest and most common types of motors used in various applications. DC motors come in different types, such as brushed and brushless, but all operate on the basic principle of electromagnetism. The working principle of a DC motor is based on Fleming's left-hand rule and the interaction of magnetic fields, specifically how a current-carrying conductor experiences a force when placed in a magnetic field. Here's a detailed breakdown of the working principle. 1. Electromagnetic induction. When current flows through a conductor, like a wire or coil, it generates a magnetic field around it. In a DC motor, the rotor, also known as the armature, consists of a coil of wire, and the stator, the stationary part, creates a permanent or electromagnetic field. 2. A force on a current-carrying conductor. According to Fleming's left-hand rule, when a current-carrying conductor is placed in a magnetic field, it experiences a force. The direction of this force can be determined using the left-hand rule. Thumb indicates the direction of the force, motion of the conductor. First finger points in the direction of the magnetic field from north to south. Second finger represents the direction of the current from positive to negative. This interaction between the magnetic field of the stator and the magnetic field generated by the current flowing through the rotor coil produces a force that pushes the rotor to rotate. 3. Continuous rotation, commutator and brushes in brushed DC motor. In a brushed DC motor, the rotor coil needs to continue rotating in the same direction. This is where the commutator and brushes come into play. The commutator is a split ring that is connected to the ends of the rotor coil and rotates along with the rotor. Brushes are stationary contacts that provide electric current to the commutator. As the rotor rotates, the commutator reverses the current direction in the rotor coil every half turn. This ensures that the force on the rotor remains in the same direction, allowing it to keep rotating continuously. 4. Torque production. The interaction between the rotor's magnetic field and the stator's magnetic field produces torque, which causes the rotor to spin. The amount of torque depends on several factors: strength of the magnetic field, stator and rotor, current through the rotor coil, number of turns in the rotor winding, the size of the motor. The faster the rotor spins, the more torque is produced, enabling the motor to perform mechanical work, such as turning a fan or driving a vehicle's wheels. 5. Speed and direction control. The speed of a DC motor can be controlled by varying the amount of input voltage or current. The higher the voltage, the faster the motor spins. The direction of rotation can be reversed by reversing the polarity of the input voltage. Key points in the working of a DC motor. Current passes through the armature, rotor, windings. The magnetic field from the stator interacts with the rotor's magnetic field. A force, torque, is produced on the rotor, causing it to turn. The commutator reverses the current direction every half turn, ensuring continuous rotation. Brushless DC motors. In brushless DC motors, BLDC, the commutation is done electronically using sensors and controllers instead of brushes and a commutator. This eliminates wear and tear and makes the motor more efficient, with reduced maintenance. Summary. The working principle of a DC motor relies on the interaction between magnetic fields created by current flowing through the rotor and the magnetic field of the stator. This interaction generates a force that causes the rotor to rotate. In brushed DC motors, a commutator reverses the current direction to maintain continuous rotation, while brushless DC motors use electronic controllers to achieve the same result. Key components of a DC motor. Stator. The stator is the stationary part of the motor that generates a magnetic field. It can consist of permanent magnets in small motors or electromagnets in larger motors or industrial applications. The magnetic field from the stator interacts with the current-carrying rotor to produce torque. Rotor, armature. The rotor, also called the armature, is the rotating part of the motor. It consists of a coil of wire wound around a core. When electric current passes through the coil, it creates a magnetic field, which interacts with the stator's magnetic field to produce motion. The rotor rotates due to the force produced by the interaction of magnetic fields. Commutator. The commutator is a split ring connected to the rotor's coil. Its primary function is to reverse the direction of current flowing through the rotor windings every half-turn of the rotor. This ensures that the rotor keeps rotating in the same direction. The commutator works in conjunction with the brushes to maintain the current flow. Brushes. Brushes are stationary components that make physical contact with the rotating commutator. They are typically made of carbon or graphite and act as the connection point for the external power supply. The brushes transfer the DC current from the external source to the rotor's windings through the commutator. Power supply, DC source. The power supply provides the direct current needed for the motor to function. It can be a battery, DC generator, or DC power supply. The power supply provides the necessary current that flows through the rotor windings, creating the electromagnetic field needed for motion. Field windings. In motors with electromagnetic stators, the stator contains field windings, which are coils of wire. When current flows through these windings, they generate a magnetic field. This magnetic field interacts with the rotor's field to produce the necessary force for rotation. Not used in permanent magnet DC motors, PMDC, but common in shunt wound, series wound, or compound wound DC motors. Shaft. The shaft is the central rod that rotates along with the rotor. It extends out of the motor casing and transfers the rotational energy, mechanical power, generated by the motor to an external load, such as wheels or gears. Frame or housing. The frame, also called the motor casing, protects the internal components of the motor and provides structural support. It often helps with heat dissipation and can sometimes have cooling features like vents or fans. Optional components. Bearings. Bearings support the rotor shaft and reduce friction as it rotates, allowing smooth and efficient movement. Cooling mechanism. In larger DC motors, a cooling mechanism, like a fan or cooling fins, is used to dissipate heat generated during operation. Summary of components. Component function. Stator generates the magnetic field, either permanent magnets or electromagnets. Rotor, armature, rotates due to the interaction with the magnetic field. Has windings where the current flows to create motion. Commutator reverses current direction in the rotor, ensuring continuous rotation in the same direction. Brushes transfer electric current from the power supply to the rotor via the commutator. Power supply provides the DC power needed to run the motor. Field windings generate the magnetic field in motors that do not use permanent magnets, only in some types of motors. Shaft transfers rotational energy from the motor to the external mechanical load, e.g., gears, wheels. Frame, housing, protects and supports the internal components, sometimes aids in cooling. The functioning of a DC motor involves the conversion of electrical energy from a direct current power supply into mechanical energy, rotational motion. This process is based on the principle of electromagnetism, where the interaction between the magnetic fields generated by the stator and rotor causes motion. Step-by-step functioning of a DC motor. 1. Power supply, DC source. When a DC power supply, battery or DC source, is connected to the motor, current flows into the armature windings, the coil of the rotor, through the brushes and commutator. This current generates a magnetic field around the rotor, armature, as every current-carrying conductor creates a magnetic field. 2. Magnetic field interaction. The motor has two key magnetic fields. Magnetic field of the stator. This field is created either by permanent magnets or by electromagnets, field windings in some DC motors. Magnetic field of the rotor, armature. As current passes through the rotor's windings, it creates a magnetic field around the rotor. These two magnetic fields interact, creating forces that push the rotor to move. 3. Fleming's left-hand rule. Fleming's left-hand rule helps determine the direction of motion. According to the rule, thumb, direction of motion or force on the conductor, rotor. First finger, direction of the magnetic field, from north to south in the stator. Second finger, direction of the electric current, flowing through the rotor. When current flows through the rotor's windings, the magnetic field produced by the rotor interacts with the stator's field. This interaction generates a force, torque, which makes the rotor turn. 4. Rotation of the rotor. The rotor starts rotating because the torque produced pushes it in one direction. The rotor will continue rotating as long as the force keeps acting on it, converting electrical energy into rotational mechanical energy. 5. Commutator and brush system, 4-brushed DC motor. The commutator is a split ring connected to the rotor's coil and rotates along with the rotor. As the rotor turns, the commutator reverses the direction of the current in the coil at regular intervals after every half turn of the rotor. This ensures that the torque, force, on the rotor continues to push it in the same direction, resulting in continuous rotation. Brushes are stationary contacts that transfer the current from the power supply to the commutator and rotor windings. They ensure that current flows into the rotor coil, creating the necessary electromagnetic field. 6. Continuous rotation. The rotor keeps rotating as long as current flows through the armature windings, and the commutator ensures that the rotor's current is reversed at the appropriate intervals. The continuous interaction between the rotor's electromagnetic field and the stator's magnetic field generates rotational motion, which can be used to drive mechanical devices like gears, wheels, or belts. 7. Speed control. The speed of a DC motor can be controlled by adjusting the input voltage. Increasing the voltage increases the current in the rotor, which strengthens the magnetic field and increases the motor's speed. Varying the current in the field windings. For motors with field windings, changing the strength of the stator's magnetic field also affects the motor's speed. 8. Torque generation. The torque generated by the motor is proportional to the current flowing through the rotor's windings and the strength of the magnetic field. Higher current or stronger magnetic fields will produce greater torque, which is essential for applications requiring more power at startup, like electric vehicles or cranes. 9. Mechanical output, shaft rotation. The rotating rotor is connected to a shaft. The shaft transfers the rotational mechanical energy from the motor to drive an external load, such as a fan, wheel, conveyor belt, or other mechanical device. Summary of functioning. DC current flows through the rotor, armature, windings, creating an electromagnetic field. The rotor's electromagnetic field interacts with the magnetic field of the stator. This interaction produces a force, torque, that causes the rotor to rotate. The commutator reverses the direction of current in the rotor windings, ensuring continuous rotation in one direction. The motor continues rotating as long as there is a current, and the mechanical energy, rotation, is transferred through the shaft to perform useful work. Key points in the functioning of a DC motor. Current flow. DC power supply sends current through the rotor coil, creating a magnetic field. Magnetic field interaction. The rotor's magnetic field interacts with the stator's magnetic field to create torque. Commutation. The commutator reverses the current direction in the rotor, ensuring continuous rotation. Mechanical output. The motor's rotational motion can drive external devices, like wheels or fans. DC motors come in different types based on their design and the way the stator's magnetic field is generated. These variations cater to specific applications, offering distinct advantages in terms of speed control, torque, efficiency, and maintenance requirements. Types of DC motors. 1. Brushed DC motors. In a brushed DC motor, the rotor windings receive current through brushes that make contact with a commutator. This type of motor is the simplest and most common form of DC motor. Key features. The rotor is equipped with windings, and the stator may consist of either permanent magnets or field windings. The commutator reverses the current direction every half turn, ensuring continuous rotation. Subtypes of brushed DC motors. Shunt wound DC motor. Connection. The field windings, stator, are connected in parallel, shunt, with the armature, rotor. Characteristics. Provides constant speed regardless of load. Lower starting torque compared to series wound motors. Applications. Lathes, conveyors, fans, and general industrial machinery requiring steady speed. Series wound DC motor. Connection. The field windings are connected in series with the armature windings. Characteristics. High starting torque, making it ideal for heavy load conditions. Speed decreases significantly with increasing load. Runs at dangerously high speeds under no load. Applications. Cranes, hoists, electric locomotives, and other heavy-duty machines. Compound wound DC motor. Connection. Has both series and shunt windings, combining the benefits of both types. Characteristics. Moderate starting torque and relatively constant speed under load. More versatile than either series or shunt motors alone. Applications. Elevators, presses, and rolling mills where both high starting torque and speed regulation are needed. Advantages of brushed DC motors. Simple and inexpensive. Good for applications requiring high starting torque. Easy to control speed by varying input voltage. Disadvantages. Brushes and commutator wear over time, requiring maintenance. Generate sparks and noise due to the mechanical contact of brushes and commutator. 2. Brushless DC motors, BLDC. Brushless DC motors, BLDC, operate without brushes and a commutator. Instead, they use electronic commutation via sensors and controllers to switch the current in the stator windings. Key features. The rotor is made of permanent magnets, and the stator consists of coil windings. Electronic sensors detect the position of the rotor and switch the current in the stator coils accordingly to maintain continuous rotation. Advantages of BLDC motors. High efficiency and reliability. No brushes mean less wear and tear, making them longer lasting and more efficient. Low maintenance. Without brushes, there are fewer components that require servicing. Quiet operation. No mechanical friction due to brushes. Better speed and torque control. Electronic control provides precise speed regulation. Applications. Hard drives, cooling fans and computers. Electric vehicles, drones, and robotics. Industrial automation, servo motors. 3. Permanent magnet DC motor, PMDs. Permanent magnet DC motors use permanent magnets in the stator to create the magnetic field, eliminating the need for field windings. Key features. Simpler construction since there are no field windings, resulting in a more compact and lightweight motor. Typically smaller in size than other types of DC motors. Advantages. High efficiency due to the absence of field windings. Less energy loss and low current consumption. Compact size makes them suitable for small devices. Disadvantages. Limited torque compared to motors with electromagnetic fields. Expensive due to the cost of high-performance permanent magnets. Applications. Small household appliances like electric toothbrushes, toys, and fans. Automotive applications, including power windows and windshield wipers. 4. Series parallel DC motor, universal motor. Universal motors can operate on both AC and DC power. They have a series wound configuration, meaning the field and armature windings are connected in series. Key features. High starting torque. Like series DC motors, they provide strong torque at startup. Operates on both AC and DC power. Advantages. High-speed operation. Suitable for both AC and DC sources, making them versatile. Compact and lightweight for their power output. Disadvantages. Requires frequent maintenance due to brush and commutator wear. Can be noisy. Applications. Handheld power tools, drills, saws, kitchen appliances, blenders, vacuum cleaners, and hair dryers. 5. Self-excited DC motor. In a self-excited DC motor, the current that energizes the field windings is generated by the motor itself. There are two main subtypes. Shunt-excited DC motor. The field winding is connected in parallel with the armature. Series-excited DC motor. The field winding is connected in series with the armature. These types of motors are more stable compared to separately excited motors, but are mostly used in industrial setups where excitation is internal to the motor. Summary of DC motor types. Motor type. Key features. Applications. Brushed DC motor. Simple. Uses brushes and commutator fans, conveyors, automotive systems. Brushless DC motor, BLDC. No brushes, electronic commutation, high-efficiency electric vehicles, drones, computers, industrial robotics. Permanent magnet DC motor uses permanent magnets for the magnetic field. Toys, household appliances, automotive systems. Series wound DC motor. High starting torque. Series connection. Cranes, hoists, trains. Shunt wound DC motor. Constant speed. Shunt connection. Lathes, industrial machinery. Compound wound DC motor. Combination of series and shunt windings. Elevators, rolling mills. Universal motor runs on both AC and DC. High-speed operation. Power tools, blenders, vacuum cleaners. Each type of DC motor is suited for specific applications based on factors like required torque, speed control, efficiency, and maintenance. DC motors are used in a wide variety of applications because of their ability to provide high starting torque, easy speed control, and reliability. Depending on the type of DC motor, its characteristics make it suitable for specific tasks in both industrial and domestic settings. Applications of DC motors. 1. Shunt wound DC motor applications. These motors offer constant speed and are suited for applications where steady speed is critical, even under varying loads. Industrial fans. Shunt wound motors maintain a consistent speed, making them ideal for driving fans that require steady airflow. Conveyors. Used in conveyor systems where speed consistency is important for moving goods. Lathe machines. The constant speed feature ensures precise cutting operations. Blowers and pumps. Shunt motors maintain a uniform speed to ensure consistent fluid or airflow. 2. Series wound DC motor applications. These motors provide high starting torque, making them ideal for heavy-duty applications that require high power at startup. Electric locomotives. Series motors are widely used in trains and trams due to their ability to provide a large torque at low speeds. Cranes and hoists. These motors are used in lifting equipment where the load requires significant force to start moving. Electric cars. In some older or low-budget electric vehicle designs, series motors are used for their high torque capabilities. Elevators. Require significant power to lift heavy loads, especially when starting from a stop. 3. Compound wound DC motor applications. Compound motors offer both good starting torque and speed regulation, making them versatile for a range of applications. Rolling mills. In metal processing, compound motors are used for their ability to provide high torque and speed control, ensuring consistent production. Presses. Industrial presses require high torque to start the pressing operation and speed regulation to control the process. Elevators. Besides series wound motors, compound motors are also used in elevators for better speed regulation under load. Mixers and agitators. Used in industries where a combination of high starting torque and stable speed is necessary for consistent operation. 4. Permanent magnet DC motor, PMDC, applications. These motors are compact, efficient, and low cost, making them ideal for small-scale applications that require lower power. Automotive applications. Windshield wipers. PMDC motors are used in wiper systems because of their compact size and ability to provide the necessary torque. Power windows. They power the window-raising mechanism in cars. Heating, ventilation, and air conditioning (HVAC) used in small fans and blowers within the vehicle. Starter motors. For starting the engine in small vehicles. Toys. Due to their small size and simplicity, PMDC motors are commonly used in toys like remote-controlled cars. Small appliances. Devices such as hairdryers, electric toothbrushes, and portable vacuum cleaners utilize PMDC motors for their reliability and size efficiency. 5. Brushless DC motor, BLDC, applications. Brushless DC motors are highly efficient, reliable, and require less maintenance, making them suitable for precision and high-performance applications. Electric vehicles, EVs. BLDC motors are increasingly used in modern electric vehicles due to their high efficiency, long lifespan, and low maintenance. Drones and UAVs. BLDC motors offer high power-to-weight ratios, making them ideal for powering drones and unmanned aerial vehicles. Computer hardware. Hard drives. Used to spin the disks at precise and high speeds. Cooling fans. Employed in computers and other electronic devices to maintain temperature regulation with minimal noise. Industrial automation. BLDC motors are commonly used in industrial robots, servos, and precision manufacturing equipment where control and efficiency are critical. Medical devices, such as motorized surgical tools, infusion pumps, and ventilators that need precise control and reliability. Home appliances, high-end vacuum cleaners, refrigerators, and washing machines use BLDC motors for their durability and energy efficiency. 6. Universal motor applications. Universal motors can operate on both AC and DC power and are capable of high-speed operation, making them ideal for handheld devices. Power tools. Drills, grinders, and saws. Universal motors provide high speed and torque, making them suitable for high-power tools used in construction and manufacturing. Kitchen appliances. Blenders, mixers, and food processors. The high speed and torque provided by universal motors make them perfect for high-performance kitchen equipment. Vacuum cleaners. Universal motors are used in vacuum cleaners due to their compact size and ability to run at high speeds. Hair dryers. Universal motors drive the fans and heating elements in hair dryers for effective heat distribution. Applications by industry. Automotive industry. Windshield wipers, power windows, seat adjusters, HVAC blowers, and starter motors in cars use small DC motors for specific tasks. Household appliances. Vacuum cleaners, blenders, mixers, washing machines, and fans rely on various types of DC motors for their compactness and speed control features. Robotics and automation. Servo motors, often BLDC motors, are used in robotic arms, CNC machines, and automation systems where precise control and efficient operation are necessary. Medical devices. DC motors power infusion pumps, prosthetics, motorized wheelchairs, and surgical devices, providing reliable and controlled movement. Industrial equipment. Cranes, conveyors, presses, elevators, and pumps use DC motors, particularly in heavy-duty environments where consistent speed control and high torque are important. Conclusion. DC motors are crucial in a wide range of industries, including automotive, industrial, household, and robotics, because of their versatility, reliability, and ease of speed and torque control. Whether in compact devices like toys or large machines like cranes, DC motors offer specific advantages for each application type.